Hi, I'm Luke McDonald. I'm an ASM.
I'm Dan Entile, ASM major.
I'm Kurt Hubble, ASM. We did the ADM, ground fire, pile, fan control.
Kurt, give me an overview. I see what this is a modern ground pile. Of course, it's not the real thing, which is several hundred feet in diameter. But what is the overall problem that you're trying to solve?
Well, they wanted to solve a wind cost, or not wind cost, energy cost. And with typical ground pile, the fans are on all the time. All the fans, all for the 6 months that they're down, 4 months, whatever, when they don't really need to be on.
So we have an idea of how much that costs?
Well, we had a study earlier in the year from there for a variable rate drive fans that it's $40,000 a year in energy costs for just one ground pile.
One pile.
$40,000.
And there's 3 piles on this location.
So energy cost is their major cost for the ground pile right now. Our system uses an anemometer and a PLC. The anemometer tells PLC what the wind speed is, and the PLC determines what fans need to be on. We have 4 different stages. Stage 1, we have 4 fans on at all times, no matter what the wind speed is. Stage 2, we have 4 more fans coming on. Stage 3, we have 4 more, and then stage 4 is all the fans on.
Okay, so the logic here, I'm assuming, is when wind blows, there would be a tendency for this cover. Is it plastic?
Yeah, plastic, tarp material.
Heavy duty tarp.
Yeah, heavy duty tarp. Yeah.
When the wind blows, there's a tendency for it to come off. So the purpose of the fans is suction to draw it down to the ground.
Yep.
And the simple logic is more wind, you need more suction.
Yep.
I get it. So what we have here, it looks like this is a real controller.
Yeah.
But it's not a real pile.
Right.
Right. So Dan, tell me, this looks like real logic.
It is.
So you're gonna have to sort out what about this is real, what about this is fake.
Okay, well this is fake. There's not going to be corn falling out of this pile.
Okay.
But the logic is real. It's on my computer back behind here. This is just the beginning stages, your start and stop switch, which turns the system on, and then you have rungs on there for if the power fails. You have the generator, which is BGen, and then you have timers turning fans on in stages so that they don't draw current at the same time.
Because if we turn more than one on at once, there's the current surge, spike, it costs you more per kilowatt hour.
Right, and you could potentially damage fans. And then based on the wind conditions, we use data collected from the State Climatology Office here at Purdue. This was for Grissom Air Base. It's the closest site that we could get information on, and that's 20-year data of the wind speeds in that location for the time that the ground pile would be active, that they would have rain.
What kind of software did you use to draw a graph like that?
That is WS plot software, some fancy meteorology software.
I'm really good at Excel, because I don't think I can make Excel do that.
I don't think so. You could download, you could get the data from this program onto an Excel file. So.
Yep, and I love this. Did you learn that in a course at Purdue, or did you just?
We just touched real shortly on it, and we kind of taught ourselves with the help of another instructor.
Yeah, so that's what education is.
So this
exposure. Realize you got to learn on your own.
Right. This was definitely a learning experience. You know, learning the logic, because we didn't really have any clue before we started this project.
It's one of the things I love about Purdue, about engineering and agriculture. It's the can-do attitude. It's fancy. Looks like Christmas. It's warm. It's not Christmas time in Indiana. Luke, tell me what's going on here. Give us a little demo.
All right. Well, right here we have 16 relays. And each relay is these simulate the motor relays. So each LED on this pile here represents a fan. This one is lit because that fan would be on.
Always 4 fans are on.
Correct. These fans are just for another visual of which fans are on.
Just like the dashboard in the office. What's going on out there?
Yeah.
Gotcha. So turn up the wind. Let's see what happens.
All right.
Woo!
We had something nicer.
Let's go to Kansas or something.
But if you shine on there, you can see the lights kick on.
got
The
one.
next one will divide those two. Like if you move up 4.
This one's gonna come on next?
Yep.
Yep. Because one comes on, gets up to speed. In theory, another one will come on. All right, I get it. So these are the timer delays.
Yeah.
Yep. All right. And if it got even windier, then we come back and turn more on. I get it.
Yep.
That's nice.
That last one came on. And now, seeing as how if you have a gust of wind, you don't want your fans to be turning on and off. We have it stay in this stage for 30 minutes, but for the purpose of this display, we only have it going for 30 seconds. I don't know.
Gotcha. So we're not looking at on and off instantly. We're looking at kind of a steady.
Because that would just put so much you damage your fans over time doing that and your motor starters.
So each one of these fans, about how many horsepower would they be?
7.5.
7.5 horsepower each.
Those fans should be turning off. They just turned off.
Yep, these did all come back off because the wind died down.
Right.
And
Okay, why don't we simulate if the generator comes on, if you lose power.
Okay.
Lose power.
So if in a situation where you lose power
Don't turn on.
and the generator would kick on, that's usually a situation where there's bad weather, severe weather.
right,
So,
that's when you need the
Yeah.
fans.
so if the generator kicks on, it also sends a signal to the PLC here to fire every fan on.
Right.
In sequence,
Yep.
not all at once,
Right.
especially when on generator, I suppose.
Right, because all the fans continuously come on.
Right. So phase in. Oh, that's great. So you talked earlier about $40,000 a year in energy cost. How much would we expect? I realize it's maybe a from the hip projection, but how much should it energy costs be with the new and improved system?
We're looking to save what we paid for the project the first year, so have a full payoff for the project. So
100% return on investment.
right. So we're looking
1
to
year
hopefully-
payback.
Right.
Second,
Save
third, and fourth
$13,000.
year, it's all
Right.
icing,
Right.
profit.
Right.
Pretty cool. So Kurt,
Yes.
obviously the most complicated, difficult part of this project.
I'd say definitely the PLC. Programming the PLC. Yes. The logic was very difficult. As an ASM student, we don't have very many classes on programming, but luckily with the help of technology, teachers, professors, we got a lot of help from them.
Good
Got
help.
it working. Yeah.
Okay, just real quickly, just to end, let's go around the room. When do you graduate?
In May this year,
Do you have a job?
work for ADM.
I'll be graduating next semester. in the fall.
And what are you doing this summer?
This summer I'll be interning with ADM in Louisiana.
I'm going to be graduating this May, and I'm still looking. Hopefully soon going to have a job.
Very good. So here we are at Purdue Ag and Biological Engineering. We do machine stuff, we do biological stuff, we do grain stuff, but we always solve problems.